Hello friends, I am Snehal and I am teaching you physics. In last two lectures, we studied about position versus time graphs, velocity versus time graphs and kinematical equations of motion. In today's lecture, we'll see some problems based on those topics. So let us start. We'll see a simple problem. First one, identify which of the following graphs curves possibly represent motion. And curves are like this. First one is position versus time, just like this. A, then this is V versus T. V versus T, it is like this. This is V. The next curve is distance covered versus time, and curve is like this, C, and the last curve is position versus time, and it is like this. Okay, so what do you think? This curve represents motion or it doesn't represent? So answer is no, and the reason is, if we take some time, suppose this is any time t, okay, from here to this point, then you will find that at this time the object is having these two positions. If we try to find position of an object, we get these two answers, x1 and x2. And we know that no real object can have two positions at the same time. The object cannot be simply here and there at the same time. So that's why this graph must not represent motion. It doesn't represent. What about this graph? Here this is velocity versus time graph, and the case is same as that of here. If we take any time from here to here, let's say this time, we get these two velocities. This is v1 and this one is v2. So we get two velocities, one of which is positive and another is negative. So the object cannot be moving in two different directions at the same time. So this graph also does not represent motion. This is wrong. What about this graph? The distance covered versus time graph. In this graph, we know that the distance covered should always go on increasing. Okay, if there is any object, the distance covered by object is just total path length, and because it is total path length, it keeps on increasing and increasing only. And in this graph, you can see that the distance covered here, it is decreasing from this point. So this graph also does not represent motion. And the last graph, yes, this one does represent motion. It is just position versus time curve for an object which is moving in oscillatory motion. It is moving like this. So position is changing like this versus time. So given some graphs, we should be able to identify which of them represent real cases, the cases of motion of real objects, and which one do not represent. So this is how we will find out. Okay, let's move on to the next problem. Another simple problem. and problem is an object moves in a straight line and in same direction. It displaces, it covers distances of s1 with velocity v1, then s2 with velocity v2, and s3 with velocity v3 in same direction. Find average velocity. Okay, so here is an object which is moving distance s1 with velocity v1, s2 with velocity v2, and s3 with velocity v3, and we have to find average velocity of object. Suppose this is straight road, this is an object, person running on this road goes up to here with velocity v1, then from here to here it moves with velocity v2, this is s2, and this is s3. With velocity v3. Okay, now we know that the average velocity equals to the total displacement divided by time. Average velocity is displacement divided by time, and total displacement of this object from start position is the sum of these three. It is s1 plus s2 plus s3, and suppose the time taken be t1 in this case, t2 in this case, and t3 in this case. So I can write average velocity av equals to total displacement, which is s1 plus s2 plus s3 divided by times t1 plus t2 plus t3. Okay, after that we need to find these times t1, t2 and t3. So for that we know this formula, that velocity is equal to displacement divided by time. So v1 equals to, I can say, s1 upon t1. It gives me t1 equals to, if I take t1 on this side, v1 on the other side, I will get t1 equals to s1 divided by this v1. And similarly, I can write the t2 equals to s2 divided by v2, and t3 equals to s3 divided by v3. Then we'll use these values of t1, t2 and t3, substitute them here. So what do we get is the average velocity is s1 plus s2 plus s3 divided by s1 upon v1 for this t1, then plus s2 upon v2 plus s3 divided by v3. Okay, so you may come across a numerical where the numerical values of these quantities s1, s2, s3, maybe t1, t2, sorry, v1 and v2 and v3 are given. So even in that case, you will solve problem like this, and only at the last step you will substitute numerical values. Otherwise, the problems become very difficult to solve. So this approach we'll use. Okay, now let's see next problem, a numerical problem. So problem number 3, and I will erase this. Okay, so problem number 3 is, suppose there is a car moves or it accelerates from, let's say, 36 kilometers per hour. I'm taking the simple values to 72 kilometers per hour in, let's say, okay, I will not take time, while covering distance of 20 meters. Okay, so there is a car which accelerates from 36 kilometers per hour to 72 kilometers per hour while covering a distance of 20 meters in same direction. And we'll take this simple problem. Find acceleration of the car. Okay, so let's note down whatever quantities, the values we have. So we have this initial velocity, which is 36 kilometers per hour. Then we have this final velocity, which is 72 kilometers per hour. And we have a distance covered in same direction, that is displacement is 20 meters. Okay, now you can notice that u, which is initial velocity, is 36 kilometer per hour. V is the final velocity and it is 72 kilometer per hour, and S is displacement, it is 20 meters. Now the units of these quantities are different. This one, the speed or velocity is given in kilometers per hour, and the distance or the displacement is given in meters. So we have to convert all the quantities in same sets of units. So we are going to use units, the SI units, that is standard units for this the distances are meters, and for time the standard unit is seconds. So we'll convert these velocities from kilometers per hour to meters per second. So let's do that. And I know that 1 kilometer, 36 as it is, 1 kilometer equals to 1000 meters. Okay, so I have substituted 1000 meters for this 1 kilometer. And 1 hour is equal to 3600 seconds. 60 minutes, 1 hour is 60 minutes, and 1 minute is 60 seconds. So 60 times 60 is 3600. Then we can cancel out the zeros, and what do we get is 10 by 36. Or I can take 2 common from numerator and denominator from here, so I get 5 by 18. Okay, so whenever I convert from kilometers per hour to meters per second, I will multiply by 10 by 36 or 5 divided by 18. Okay, so here 10 by 36 is more useful because this just gets cancelled out, and what do I get is 10 meters per second. This is 72 multiplied by 10 divided by 36, and 36 2s are 72, so 2 10s are 20, so I get 20 meters per second. 20, and S is 20 meters. Okay, so let me just rewrite this. U equals to 10 meters per second, V equals to the 20 meters per second, and s equals to 20 meters, and we have to find what is the acceleration. Now it's quite straightforward. We have to use a kinematical equation of motion. And which equation? The equation containing u, v, s and a, that is the third kinematical equation, which is v square minus u square equals to 2as. And we have to find a, so let me take that a on other side. Let me keep a alone and take 2s on other side. So a equals to, if I take 2s on other side, it is v square minus u square divided by 2s. Now let's substitute values. V is this 20 meters per second. So 20 squared minus u is 10 meters per second. So 10 squared divided by 2 times this s, and s is 20. So let's multiply this out. Let's solve this. 20 square is 400 minus this 100 divided by 2 times 20 is 40. And this is 300 divided by 40. This gets cancelled. 30 by 4. And I guess this is 7.5 something. Yeah, 7.5 meters per second square, because this is acceleration. Okay. Yeah, so this was a simple problem. Let's move on to next one. Problem number 4. Find ratio of displacements covered by freely falling object in successive equal intervals of time, and it is given that initial velocity of this object is 0. Okay, so we have got an object which is freely falling from some height. Its initial velocity is 0, and we have to find the displacements covered by object in successive equal intervals of time. So let us do that. So displacement, suppose this is our object dropped from here, and let's say in time t it moves till here, till this point, and let me call this s1. Okay, so displacement in first interval of t will be given by, so we know the formula for displacement is s equals to ut plus half at squared, and because u equals to 0, so we have this s1 equals to, the u is 0, it is just half a times t squared. Okay, then in next successive time interval, suppose object goes from here to here, so it will be s2. So this much distance is also covered in next time interval t. So now what we'll have to do to find out this displacement is that we'll find this total displacement s1 plus s2, which is covered in time 2 times t, and we'll subtract this much distance. So I will find distance covered in 2t, so which will be s2, which is equal to half of a into 2t squared, and 2t squared is 4 times t squared. So I will take 4 on this side, so it is 4 times half of at squared. And we know that this half at squared is s1. So I will write s2 equals to, okay, let me not write this as s2, it is just distance covered in 2t. I will not denote it by anything. So it is just 4 times s1. And the displacement in second time interval t, it will be this total distance, which is 4 times s1, minus this displacement in first time interval, okay, t. So I can write displacement in second time interval of t is equal to displacement in 2t minus displacement in t, and it is, and I will denote this by s2, and it is 4s1 minus s1, which is 3 times s1. Good. Now let's find displacement in next time interval, and for that we'll need displacement in 3t. So we'll find that displacement in 3t, we'll subtract this out, and we'll get displacement in third time interval t. So I can write distance covered, okay, let me keep some space here, distance covered in 3t, from 0 to 3t, or from 0 to 3t. It is just half of a into 3t squared, and square of this is 9 times t square. I will take 9 on this side, and I will write this as 9 into half of at square, and we know half at square is equal to s1, so this is 9 times s1. Then I have to find displacement in time interval, third time interval, okay, t. So I can write displacement in third interval, third successive interval of t is equal to displacement from 0 to 3t minus displacement from 0 to 2t. So we will get displacement from 2t to 3t. Okay, so this is equal to 9s1. I will erase this too. Minus displacement in from 0 to 2t, we found here it was 4 times s1, so it is 9s1 minus 4s1. It was here displacement in 2t, 4s1, so this is going to be 5 times s1, and I will represent this by s3. Okay, so suppose displacement in time interval t is s1, displacement in next time interval, we'll call it s2. It is, we know it is 3 times s1, and we just found that displacement in next time interval is going to be 5 times s1. So ratio is therefore ratio of displacements in successive time intervals is going to be s1 is to s2 is to s3 is, and so on. Okay, it is 1, s2 is 3 times s1, so 1 and is to 3:5 is to, and so on. So it is going to be 7 and so on. Okay, and this thing has got a name. It is called as Galileo's law of odd numbers. So this is Galileo's law of odd numbers. Good. And the beauty of this is we did not use G. We just wrote S equals to half of AT squared. We didn't care whether this A is 10 meters per second square or it is 15 meters per second square. Whatever it is, if object is accelerating uniformly, then the displacements, the ratio of displacements in equal successive intervals of time is going to be the ratio of these odd numbers 1:3:5:7. So this is the beauty. It may be gravitational motion or any other accelerated motion. Okay, so we can use this result. This is an important result. So let us put a box here. So ratio of displacements in successive time intervals in case of uniformly accelerated motion. Okay, so we solved few problems here, and next thing to do is that you are going to solve lots of problems, and in next lecture we'll see some basic calculus, the differential calculus. Thanks for watching this lecture.